Hi everyone. So this is Jakob's recent talk, but unfortunately he couldn't make it today. So I'm substituting for him. This is a joint work by Jakob, Nikolai, and myself. I'm presenting about this software tool that we're developing, CUQIpy, Computational Uncertainty Quantification for Inverse Problem in Python. And the image that comes to mind maybe when seeing this is CUQIpy, actual CUQIpy. So the cookies is an ongoing theme with our project. This software tool is part of a bigger project, which is the Cookie project funded by the Willem Foundation. And so we are developing this tool in collaboration with other group members as well. This is the Cookie project members team photo in Helsinger last year. This project started 2019 and it's going until 2025. Our principal investigator is Professor Christian Hansen. What is the aim of this software component of the Cookie project that is led by Jakob and the core developer Nikolai and me? We want to develop a software component that takes care of quantifying the uncertainties for researchers. So researchers can focus on modeling their own forward problem or on Bayesian problem, and then we take care of sampling and things like that. While at the same time, we want to give the non-expert users in the UQ framework who work on inverse problems simple interface, and we want to give advanced user full control so they can configure the software tool to work for their problem. So we provide state-of-the-art tools in this framework, including interfacing with some third-party libraries. We focus also on large-scale Bayesian inverse problems with the parameter that can be millions of parameters, Bayesian parameters. And we provide a collection of test problems that user can get started with, and enable users also to add their own custom components for example, the forward model or distribution or samplers, etc. So our software is now available in this GitHub repository under the CUQIDTU project. It was released in early, we had an early release in September 2022, and it's licensed under the Apache 2 license. We work continuously with the remaining group members to kind of address the features they need for this software and incorporate their code contributions. So this is part of like how we work actually within this project. And so we, for example, arrange some hackathons where we sit together for like 2 days and then come up with some new problems, new ideas that we want to implement. This is some photos from the most recent training that we had in Helsinger, where the attendees had the chance to go through some tutorials and solve some exercises using CUQIpy and working on some mini project after that. And we were pleased to see their feedback, positive and constructive feedback. And one aspect is that some of them emphasize that it really has a very smooth user experience and well documented and easy to use. So we are hoping to keep this experience for the user of CUQIpy. This is a snapshot of the documentation page, which you also can access from the repository. And here I want to talk about the type of problems that CUQIpy address. So it's built for the Bayesian framework. So for example, if we have a Bayesian parameter, let's say in the CT or medical imaging, the X represents this image of the brain, and we have a forward model that describes how the X-rays propagate through this object, and data measured So the aim is from the data, we want to go back and inference this 2D image, for example. And here we don't write a noise component in this formula, just it's a general representation where you can think of X as like a random variable, and B will be in turns a random variable as well. So in Bayesian inversion, how to formulate this problem is through the Bayes formula. We have the posterior distribution, which is proportional to the likelihood, and the prior distribution that incorporates prior knowledge. So if we don't include the Bayesian solution, for example, and go the classic way of solving the deterministic problem, we can obtain one realization of the solution. But using the Bayesian framework, we can obtain samples from the posterior distributions. And we see here these variable images that have some resistant structures and also some variabilities. So we have more knowledge about the parameters we are inverting for. And so in CUQIpy, we focus on these main 5 steps, which is a general framework to solve, most Bayesian problems. So we want to define the forward model, and then work on defining the priors and the data distribution, sample the posterior, and analyze the posterior. So the model can be a linear model, for example, or nonlinear. Let's say the X-ray model for CT applications. The prior, let's say, for example, centered, a normal distribution centered at 0 with this covariance matrix. The data distribution, in case of, for example, additive noise, additive Gaussian noise, we can represent it as a normal distribution centered at actually the outcome of the model, the forward model applied to X. And then we want to generate the samples. So we support multiple sampling methods in CUQIpy, for example, metropolis tasting, nuts, etc. And then after that, we want to look more into the posterior, for example, computing the map point and looking at some statistics, like the mean and the confidence interval or credible interval, and so on. And so this is a unified framework, and we want the high-level interface of CUQIpy to mimic that. And I want to point out also that we enable also the user to replace any of these components with third-party library or user-defined code. So here we will be looking at 2 different problems. The first one is a linear problem, medical imaging application, or also industrial applications, where you want to study the internal structure and construct these images, for example, for a human body, or this example for pipes, subsea pipes, to study their integrity. And then the other model is based on partial differential equations. So these are 2 different problems. The models are very different, but we want to show here that in CUQIpy, we can target these 2 problems in a similar manner. So for this PDE-based problem, for example, we might be interested in quantifying the conductivity and of a medium, and we have measurements of potential or current or voltage, for example. So for the first model, we have line integral that represent the CT forward model, where B are the data collected in the detector, X is the object, and A is the forward model. And there are some third-party libraries like Astra, Integra, and core imaging libraries that help solving the deterministic inverse problems, for example, or provide the forward model for these problems. So in CUQIpy, we integrate some of these third-party libraries. So here, for example, we have a plugin that integrates cell library with CUQIpy, and then you can start up with creating this problem that is already preset. parallel beam 2D problem, and you specify things like the dimension of the problem and the phantom type, and you obtain the model. So now we have, if we print this, we have a linear cookie model, and that maps from the domain to the range image 2D to image 2D, which are internal representations in CUQIpy of the domains, and also, for example, how to go from the degrees of freedom to the function values, and how to plot a particular domain. And it tells you that the forward parameter is X here. And this is the forward problem for the PDE-based problem. So this is the PDE model. We have the measurement of the potential U, and we want to quantify the conductivity kappa. And here we have the additional parameterization of kappa through KL expansion, where it's a summation of basis functions multiplied by coefficients. And our Bayesian parameters in this case are the coefficients. And there are also third-party libraries to compute PDE models and solve them. So, for example, Phoenix. And here we have an integration between CUQIpy and Phoenix, where we can access, for example, some simple or already set up problems. For example, Poisson 2D Phoenix, and specify the domain type and some other parameters like the parameterization of the Bayesian parameters, etc. And when we print this, we'll give a similar thing to the previous CT model. It will tell us that this is a PDE model, maps the KL domain to a continuous Phoenix function range. And will tell us that the parameter here is called theta. The second step is to define the prior. The prior distribution, in this case, for example, we can choose a simple Gaussian distribution with zero mean and some standard deviation, but it needs to be aware of the actual like geometry. So we kind of pass this information about the domain geometry. And then we can sample the prior and plot. So here we see two examples when the domain geometry changes. So if the domain geometry is image 2D, we will get samples like this. But if we choose the domain geometry, our KL expansion with particular setup, we will get samples that looks like this. And then there are other choices also of priors, for example, Gaussian Markov random field, and so on. The third step is to decide the data distribution. So this is the kind of common formulation that we have when we have additive Gaussian noise. The data that we measure is the model outcome plus the noise. And we can model the data distribution with this normal distribution centered at the model outcome and with the covariance matrix of the noise. And this can be represented almost directly in CUQIpy. So you create a distribution, but here you specify the mean to be actually the model itself, and you specify it's a model of parameters X. And it will tell you that this is a Gaussian distribution that is conditional on the parameter X. So it there's the modeling capability of CUQIpy is kind of aware of the structure of the problem and can provide you information that is helpful in that sense. Yeah, and here we think of X as a random variable. And the step 4, we want to create the joint distribution and the posterior. So first we have the likelihood distribution and the prior distribution. We have joint distribution class that creates joint distribution of both. And then once we specify the data, then it becomes posterior. And once we have the access to the posterior object, we can use any of the available samplers to sample it. And there's also, we have work in progress for the UQ method for the Bayesian problem class, which is able to identify some structures and kind of propose what is the best sampling methods for these structures. And for the CT problem here, we use the linear RTO, and then for the Poisson problem, we use PCN. And this is then the fifth step. We can look at the plots or analysis of the posterior. So we integrate also CUQIpy with ARVIS for visualization. And here we can plot the mean, for example, for the CT problem of the pipe integrity problem and the mean of the conductivity field. And we can look at, for example, marginal distributions. So to summarize this part here, basically, we have solved very different problem in nature with the same structure and steps in more or less 6 lines here. And so this is kind of a simple setup for people who want to explore with the Bayesian inversion. But of course, once you want more advanced features, then you need to make more configurations. And so in this scenario, we have like a simple posterior. We don't have hyperparameters, but I just want to say that it is possible to include hyperparameters in modeling with CUQIpy. So for example, let's say if our precision of the like prior and the data distribution are hyperparameters, like this, for example, defined as this function 1 over lambda here and 1 over delta. Then we can create this type of posterior that includes the parameter, that includes the parameters and the hyperparameters in the Bayesian formulation. And then we skip samplers for this, and we can specify some particular configuration on what to use to sample each parameter. And here, for example, we plot the hyperparameters as chain plot, and then we plot the x or the solution as credible interval plot. And this is an example of a project. This is the first real-world problem that came out of CUQIpy. This is a work by a PhD student, Celia Christensen. She is working with collaborators to study the integrity of subsurface or subsea pipes. And so in this project, they needed to model the prior in a special way where they have one prior for X, which is the pipe structure, this concentric annulus, and the other prior distribution is sparsity promoting prior for that detects the faults. So if you look at, for example, the mean of each, the mean of the structure will give you something like this. If you look at the mean of the fault after estimation, it will give you something like this. And then with post-processing, we can identify some of the location in the pipe that might be fault. And here it's a zoomed in pictures for all these 6 locations. And the color of the indicates the magnitude, and the magnitude indicates how likely this is to be fault or not. So in conclusion, yeah, please feel free if you'd like to experiment with CUQIpy. So you can, in principle, pip install CUQIpy and then start using it. And you can check out the documentation in this link. And we have training material in this repository. And these are the plugins links. And so our next step in this project, we are working on 2 papers that we want to submit to describe this CUQIpy tool, one focusing on the general CUQIpy and the other on the BDA aspects. And we are working and want to increase more internal and external collaboration and try to grow the community of users. So please feel free to try it. And if you have any questions, don't hesitate to send us emails. Thank you so much.